What up, guys? It's time to actually use the total, let's say, power of the mechanical energy equation. We're going to apply it to real life problems. And we've seen Bernoulli's equation, which is a very specific type of problem, and the Torricelli's law, which is another very specific type of problem. But what will happen if we use a pump and we will use also maybe friction? We cannot use Torricelli's law and we cannot use Bernoulli's equation. We will need to use the whole equation right here. So here we go. Let's do an example. For the next system, calculate power requirement of the pump. So let's say power requirement. So this is very important. Power requirement is either in horsepowers or watts. Calculate the pressure ratio of the pump, so actually the difference between the discharge and the suction, which will be right here. So this is my problem. Let me explain you. It is a tank. Let's say it's atmospheric. Both tanks are in atmospheric pressures. We have a small length right here, which probably might be ignored. We have here a pipe, which is 3 inches pipe. We can then use the pump, use it to this 2 inches pipe, and it's about 50 feet long, and then we throw it away here. So they also tell you the fluid is not water, it's a fluid with a specific gravity of 1.84, which is relatively high. The efficiency of the pump is 60%, which means we will need to expend a little bit more energy in the pump to get the energy requirement. They tell you the diameter of A, it's about 75 millimeters. The diameter of B is about 50 millimeters. Okay, they are gentle enough to tell you that the velocity in the inlet, so let's say this one, is about 3 feet per second. So something about, if you change it to meters, is almost 1 meter per second. The length, 50 feet, is about 15.2 meters. So as you can see, guys, I hate working with English units. I prefer from the beginning start using SI units. Good. Now let's make an analysis. Let's start with the pressure of A. Pressure of A and pressure of B, as you can see, they're outside. The only pressure you can see acting here is the atmospheric. And sorry guys, we need to choose either here A or B, since the flow goes from this to here. I would recommend you to choose A in the top of the surface of this tank and B in the outlet of the pipe. If you were to choose the surface here, right here, we will need to know the height, the total height, which we don't know. We know the total height until the end of the pipe. We don't know how long is this point right here, so we cannot do the balance. You could say that you want to ignore this little piece, maybe it's, I don't know, maybe 1 feet, 2 feet, I don't know, but theoretically we shouldn't do that. We should use the point outside or the pipe outlet. Good. So since the pressure are the same, we can cancel because each one of them will cancel. I want to choose the reference point here, 0, because as you can see, these 15 feet are referenced to the point A. So we could say CA is 0, so this will convert mathematically speaking to 0. What else do we have here? Well, since this is resting, we could say the velocity is almost 0. We cannot cancel the pump because we want to calculate the pump. Okay, we'll cancel this. We cannot take this away. Actually, this is 50 feet. The velocity in B, we don't know it actually. You just know, of course, that it goes away with something, any velocity. The friction loss, I think it was given. Yeah, sorry, it was given. Friction loss is 29.9 joules per kilogram, which is about something like 3 meters of friction. If you divide this by gravity, which is 9.8, let's say almost 10. Okay. and there's no turbine or anything taking out or away work, so we are left with pump and these three guys. So you can see the pump needs to recover, first things first, the height, which is the obvious one. Second thing, it needs to add velocity, so we need the pump to add velocity here. And not only that, guys, we need to recover all the friction loss in the pipe right here. So we have this right here. So make an analysis, guys, on why do we need the pump. We need the pump to overcome the height, to give it a little bit more velocity. I mean, if you always need to give velocity if you're going to be throwing away the liquid. And of course, overcome all the friction through the pipe. Let's call this equation the master equation of this problem. Recall that velocity of B is a function of volumetric flow rate, which is Q. And recall that the equation we will use is velocity times the area. But one little detail is I don't have Q. I don't have the volumetric flow rate. It's not given. So probably you will say, well, this is not possible to do, not possible to solve. But we got one beautiful velocity right here, the velocity in the suction, which is right here. And we know the diameter in the suction, which is 3 inches or 75 millimeters. Yeah, perfect. And wait for it. Okay, we were here. So even though we don't know the volumetric flow, we can calculate it from here. We know the velocity in the suction, which is 3 feet per second, or in SI units is 0.914 meters per second. The area, it's essentially P divided by 4 times diameter to the second power. The diameter is 3 inches or... Hey there guys, probably you've been watching this course and you've been watching essentially just a section of the course. And not only that, you watch plenty of ads. If not mine, there are also YouTube ads. So if you want to get rid of those, go and register right here. Not only that, you will get also high definition content and you will be able to follow the course in a proper way. This is a way more friendly or user-friendly interface. And for instance, if you want to go and check out class 8, you will be able to read the description, get plenty of videos. So for example, you check out this video and yeah, essentially you get to see every one of these videos through these tabs. And not only that, if you want to ask any question, you can leave it here in a reply and I will answer you ASAP. 75 millimeters. We are using meters, so let's change that to meters. It's only 10 to the minus 3. All this to the second power, multiply every concept, and we get the volumetric flow rate in the suction. Okay, we got this Q, but recall that this is incompressible flow, so the volumetric flow rate is constant everywhere in the pipe. So we got our beautiful Q right here. Let's calculate this. So Q equals velocity times area. I don't have area, but I can calculate that. P divided by 4. And now be sure, guys, to use the volumetric flow rate. We want to calculate the velocity on this pipe, so we can calculate the velocity on B. So be sure to use the 2-inch pipe, which is about 50 millimeters. Right here is it. 50 times 10 to the minus 3. Don't forget to change to meter. So we get the velocity in meters. We got the volumetric flow rate in cubic meters per second. And just solve for velocity. So it will be this to the square, the second power times this, and then go dividing this. I got 2.01 meters per second. So what does this mean is that this beam is going out 2 meters per second out. Okay, nice one. So we got this number, we got the height and gravity, and we got the velocity. So technically speaking, we are done in order to get the head of the system. Let's do it. Gravity times height, which is 15.2 meters, that was given. The new velocity I just calculated is right here, 2 divided by 2, don't forget, and the loss of energy. So if you were to do an analysis, guys, this will give you meters to the second power and seconds to the second power, this one as well. And this, recall that if you change joules to kilogram, meter, second, everything on the units, you will get, once again, meters to the second power and seconds to the second power. Good. So doing this operation, I got this. And I actually, when I'm talking about the head of the system, I don't like speaking about meters to the second power and seconds to the second power. I prefer using joules per kilograms, which means I already know how much energy per unit kilogram this system is or needs. And well, before actually continuing, I want to calculate the total power. So let's check, send this dividing. And we need, the pump needs to be about 300 joules per kilogram in order to, with a 60% of efficiency, give the system the 180 joules per kilogram that it needs. So we're going to waste a little bit of energy. But remember, power equals mass flow times the head of the system or the pump requirement. But we don't have mass flow. But if you remember, mass flow is essentially just volumetric flow rate times density. The density, we have it? No, but we know it's 1.84 in a specific gravity, so just multiply by 1000, which is the density of water, and you will have 1840 kilograms per cubic meter. This is the density. The Q, yes, we got it. We calculated in other previously, and we got 7.36 kilograms per second. So let's plug this number right here, and we know the WP of the pump, this one right here. And as you can see, kilograms, take away kilograms, and you are left with joules per second, which is here. And recall that joules per second is watts. So the total power we need on the pump is about 4,887.7 watts, which I will actually report this number as 5 kilowatts. There's always better to have extra power. And yeah, essentially, guys, we are done. In letter A, let me go here. We know already the pump requirement. And this one is very, very interesting, guys. Letter B, calculate the pressure ratio of the pump pressure discharge, which is this pressure right here, and this pressure right here. And you are probably wondering, how do you get that, or why are we asked that for, or how do we even get or calculate that? Let's imagine a little bit more. Okay, remember that the mechanical energy equation can be applied at any point. We always choose this and this for convenience, but in this problem will not make any sense to do that. We need to do a balance on the suction and a balance on the discharge, which are these points right here and that's right here. So the suction will be my new point A, and the discharge will be my new point B. Okay, actually it's right here, suction, discharge. Okay, let's do a balance right here. Obviously. So guys, probably you're wondering, where do I get all the material I use, for example graphs, tables, or whatever data I've been using through. And I got all the material I'll use in the course in the library section. So for example, you need any graph, chart, or whatever media you need, it's included in here. Go to here and you will be able to, for example, find out where I get the density of common liquids, where I got ASME pipe sizing, where I get K values for fitting and valves, where or how I calculate vapor pressure, and go to the incompressible flow course, and eventually you gotta click register. We have a difference on pressure because that's the point of a pump changing pressure, so we cannot cancel PA or PB. The height of the pump will be about centimeters or something like that, so we can ignore the height of the pump. That's very common to do. Since we have different diameters, 3 inches and 2 inches, we cannot cancel the velocities, but I'm pretty sure these velocities are almost nothing, will be about 1% or even 2% maximum on the total calculation, but just for the sake of mathematics, let's leave it here. Wouldn't make sense to cancel the pump power because we have here a pump. And well, friction. Normally, guys, when we do balances on pump, we cancel friction away because normally friction is included on the efficiency. So to make it easier, let's cancel this. We are going to suppose that the guy that gave us the efficiency already took care of this, calculating this efficiency and putting the efficiency in this concept of efficiency. And well, of course, hopefully you see that there is no work going out. So we got pressure, velocity, head of the pump, pressure, velocity. Good. So let me just, I sent to the left pressure, and I sent to the right this and this. And then, since we are interested on the delta P, let's send away this density, which we do have as a number. We have right there. This is exactly just this stuff right here, and the density. Density, we know it is 1,840 kilograms per cubic meter. The total power, and this one is tricky, guys. Probably you are wondering if we should use 300. And no, if we use 300, we will need to multiply this by the efficiency. So 0.6. Or go directly. We already calculated this value right here. Density times WP is 180. Let's use that value. 180. The velocity on A, recall, is literally the velocity given in the suction. Right here, it was 1 feet per second. We changed it to meters, and it's about 0.9. No, it was 3 feet per second. Changing it to meters, it's 0.91 meter per second. We need to power it to the second power. And recall, guys, that we already calculated the velocity on this pipe. So let me go back to show you here. The velocity on B is actually the same. This velocity here, since it's the 2-inch pipe, is exactly the same velocity right here because it's still a 2-inch pipe. So we have all the numbers. We plug the numbers to the second power, 0.91 to the second power. Of course, make the difference. Divided by 2. Don't forget this negative symbol. And yeah, just do it, and you will get your difference on pressure. So delta P is essentially your P discharge minus P suction. So you are increasing almost 3 atmospheres, the pressure right here. And yep, that's everything on this exercise. If you need more exercises, guys, please go to this website, check out the courses, go to the Applied Fluid Dynamics course. Be sure to check out part number 1 because we are talking about incompressible flow, and go to this section on the basics on mechanical energy equation. You will find there many problems, exercises, solved problems, quizzes, slideshows, and much more in the library. See you in the next video. This was a free preview. You want to get full access, go to my incompressible flow course. The link is in the description of the video. You will get all access. Not only that, you get a very straightforward, user-friendly interface. So for instance, you were analyzing or studying pumps, you have it here, the pump block, and then you have the sections. If you were, for example, studying the types of pumps, you can go here, and you have all the classes right here. Not to mention that you also have introduction and conclusion of every one of these. So for instance, if you were studying positive displacement pumps, the video is right here. If you were studying positive displacement pumps in rotatory and reciprocal are also included here. Centrifugal pumps, which is a very important topic in this course, you have it right here.